So it stands to reason, all this adds together to say after oxygen you have different metals. With different metals, different enzymes, new enzymes can do new things. This is again R.J.P. Williams' prediction for what metals would do what reactions in which enzymes. But you can have all these categories. I mean, R.J.P. Williams was, he had a ton of information in his head. And I just want to show you that this is his way of getting his information out. And I think what's interesting is actually if you look at molybdenum, remember that's not just solubility. When you have the banded iron formations, that's solubility. It's becoming solid and sinking to the bottom of the ocean. Not everything changed its solubility. Sometimes it just changed its oxidation state. But it turns out that molybdenum changed from a +4 to a +6 oxidation state. And it became the only thing that could do a +6 oxidation state. But the +6 was not available before oxygen. So that's a case of a charge becoming more available. Same thing though. You're talking about electrons moving. You're talking about an E value. And molybdenum is actually used in two enzymes that actually react with oxygen-containing things. Your ethanol detoxifying enzyme and your sulfite detoxifying enzyme both use molybdenum to move oxygens around. So molybdenum is, I just want to say, it's not always solubility, but usually it's something connected to oxygen and redox potential. Another interesting thing, and this is something I would like more confirmation on, this is why it didn't get into the book, but if you actually measure the redox potential range inside organisms, you'll see an interesting thing that strict anaerobes have a negative redox potential range. And if you get to aerobes that use oxygen or require oxygen, they have a range up to 0.8. So there's an idea that as you go from the strict without oxygen to strict needing oxygen, and you have these things in the middle that sort of use these things like nitrate users. Nitrate was made by putting oxygen on nitrogen, and then those have a redox potential range that's sort of moderate. Okay? So this is something I would like more about, but the main thing is, notice the trend of upper redox potential fits with the trend of time. And by the way, I have a paper that just came out in the past year where they actually found nitrate after the great oxidation event in amounts that these organisms could use. So there's a geological confirmation that nitrate was not available until after. So is there a way to use an electrode to date an organism's time of origin? I would like to take an organism that we don't know its time of organism or origin, measure its redox potential range, and see if then we can go back and fit it into this, see if it all fits together. But again, too many experiments, too little time. The main thing is E values. And so we're talking about E values, we're talking about KSPs. And we're talking about the potential. You see this is a form of the same table that we have in Atkins. But this is given to show what's early and what's late in Earth history. And just remember the redox potential of the Earth expands from being negative to 0, from being somewhere in this range. When you have oxygen right now, our redox potential of the planet is plus 0.8. Okay? And so as life evolved, it fit this different redox environment, and different things would have happened with the chemistry. The only other thing I have to say, this should look a little familiar from Chapter 5. R.J.P. Williams will often put things in the same way that Atkins does, because they're all chemists. It's how chemists talk and think. Okay. Yeah. Yeah. In this country, R.J.P. Williams is an Oxford scholar. So it's like how they would say Z instead of Z. In fact, when I was in Canada, there's some American speaker accidentally said Z, and then he caught himself and said, "Oh, you mean Z, right?" And everyone said Z, you know. So in Canada, you'll probably see them say oxidized with an S as well. Yeah, so that's not a typo. And he does get the equations right. When you're learning these equations, these are the same things that R.J.P. Williams knew and what he worked from. So the idea is that originally the Earth allowed those reactions, but as it expanded, it allowed copper reactions, nitrate reactions, you know, manganese O2, manganese plus 4 reactions. All right? So, yeah, that's the data talk.
When did he die?
Recently, like 2012.
And you never got to meet him?
No, I never got to meet him, but I did get to meet the person I first